Hello friends, today I will discuss the speed control of three-phase induction motors by Cascade method. So the necessity of this is when there are two three-phase induction motors which are coupled and whose speed is to be controlled, in that case we have to follow certain methods. One method is called the cumulative connection, the other method is called the differential connection. Under these two conditions, it is necessary to know the what is the common speed of the motors while they are connected in cumulative mode, while they are connected in differential mode. In this video, we also cover some of the terms which were already known. Their synchronous speed is nothing but ns is equal to 120 f by p, and where f is supply frequency and p is the number of poles of the three-phase induction motor, and ns is the synchronous speed, and this is nothing but the stator magnetic field speed. Slip, this is represented by s, and that is also equal to ns minus n divided by ns. Here n is the rotor speed, and that is nothing but motor speed, or that is nothing but actual speed of the motor. Ns is the synchronous speed. This rotor speed n is related with slip and the synchronous speed like this. Rotor speed n is equal to ns into 1 minus s. And these three definitions are extended to the two three-phase induction motors which are connected in cascade here. This is the one slip ring induction motor whose slip is S1 and the number of poles are P1. And here this is the second slip ring induction motor whose slip is S2 and the number of poles are P2. And this is machine 1 and this is machine 2. Machine 1 is supplied by a three-phase supply and whose supply frequency is F, and the rotor EMF frequency of machine 1 is represented by F dash, and from the slip rings of the motor 1 the supply is drawn to the machine 2 slip ring induction motor like this, and the rotors of motor 1 and motor 2 are mechanically coupled like this via a shaft, and the induced EMF frequency of machine's 2 rotor is nothing but F double dash. For machine 1, the slip S1 can be written like this. S1 is equal to NS1 minus NR1 divided by NS1. Here NS1 represents the synchronous speed of the machine 1, NR1 represents the rotor speed of machine 1, and S1 is the slip of machine 1, and F dash is the rotor EMF frequency of motor 1, and that is related like this with the slip S1 and supply frequency, that is S1 into F, that is F dash is equal to S1 into F. Similarly, the synchronous speed of the machine 1 can be written as NS1 is equal to 120F divided by P1. So F is the supply frequency here, that is input frequency to the machine 1, and P1 is the number of poles on the machine 1, and from this the rotor speed of machine 1 can be written as NR1 is equal to 1 minus S1 into NS1, and this is represented with equation 1. Similarly, for machine 2, the connection is shown like this. This is the machine 1, this is the machine 2, but the supply that comes from here so is nothing but cumulative in nature. So for machine 2, S2 is nothing but NS2 minus NR2 divided by NS2. Here NS2 is synchronous speed of the machine 2, NR2 is the rotor speed of machine 2, and S2 is the slip of machine 2. When F dash frequency supply is connected to the machine 2, then the induced EMF frequency of machine 2 is nothing but F double dash. So that F double dash is related with the F dash like this with slip S2. F double dash is equal to S2 into F dash. Similarly, NS2, that is synchronous speed of machine 2, can be written as 120 F dash divided by P2. Here F dash is nothing but the input supply frequency to the machine 2, and P2 is the number of poles on machine 2, and F dash and F double dash is related like this. F double dash is nothing but S2 into F dash, and this F dash is related with F like this. F dash is equal to S1 into F. So substituting F dash is equal to S1 into F, the equation becomes like this: 120 S1 into F divided by P2. So from this, NR2, that is machine 2 rotor speed, can be written as NR2 is equal to 1 minus S2 into NS2. NS2 is the synchronous speed of machine 2 and S2 is the slip of machine 2. Remember here, both the rotors of machine 1 and machine 2 are coupled by common shaft, that is mechanically coupled like this. So both the rotor speeds must be same as the shaft, that is NR1 must be equal to NR2, that is NR1 is equal to NR2 is equal to, we say, shaft speed or NR, or in general it is a rotor speed. So having known the equation 1, that is for machine 1, that is 1 minus S1 into NS1, that is nothing but NR1, and NR2 is nothing but 1 minus S2 into NS2. So from this, NS1 can be replaced with 120F by P1 and NS2 can be replaced with 120 S1F divided by P2 like this. And then after further simplification, that is 120F, here 120F going to get cancelled, then the equation becomes 1 minus S1 divided by P1, and then this becomes here S1 by P2 into 1 minus S2. Then further simplification leads to like this: 1 by P1 minus S1 by P1 is equal to S1 by P2 minus S1 S2 divided by P2. Further simplification leads to S1 into 1 by P1 plus 1 by P2 is equal to 1 by P1 plus S1 S2 divided by P2. Since the slip for induction motors are very small, so S1 into S2 is very small, so this term, that is S1 S2 divided by P2, can be neglected. Then the above equation will become like this: S1 into 1 by P1 plus 1 by P2 is equal to 1 by P1, and it can be further simplified like this: S1 into P1 plus P2 divided by P1 P2 is equal to 1 by P1. So from this, S1 can be written as S1 is equal to P2 divided by P1 plus P2. So once S1 is known, NR1, that is motor 1 speed, can be written as NR1 is equal to 1 minus S1 into NS1. So S1 can be substituted like this, that is 1 minus P2 divided by P1 plus P2, and NS1 can be replaced with 120F by P1. Then after further simplification, this NR1 becomes P1 plus P2 minus P2 divided by P1 plus P2 into 120F by P1, and this P2 P2 going to get cancelled, and this P1 and this P1 is going to get cancelled. Then NR1 becomes 120F divided by P1 plus P2. That is the common speed of both the machines, machine 1 and machine 2, that is NR1 becomes NR2, that becomes NR, that is equal to 120F by P1 plus P2. Next, suppose this second machine is connected with the first machine with a differential coupling like this. This is the negative phase sequence supplied to the machine 2. And this is machine 1 as usual. Its input is 3-phase AC supply with frequency F, and the EMF rotor EMF frequency of machine 1 is F dash, and the slip of machine 1 is S1, and the number of poles on machine 1 is P1, and the slip rings of machine 1 gives the supply to the machine 2 like this, that is negative phase sequence supply like this, and the machine 2's slip is S2, and the number of poles on the machine 2 is P2, and the induced EMF frequency of machine 2 is F double dash. So for this differential coupling for machine 1, the rotor speed is nothing but NR1 can be written as 1 minus S1 into NS1. Similarly, for machine 2, NR2 is nothing but is equal to 1 minus, for negative phase sequence, this becomes 2 minus S2 into NS2. Instead of 1 minus S2, it will become 1 minus 2 minus S2. So after further simplification, machine 2 rotor speed NR2 becomes S2 minus 1 into NS2. NS2 is the synchronous speed of the machine 2. Since both the rotors are mechanically coupled by a common shaft, so both the rotor speed will be same, that is NR1 must be equal to NR2, that is equal to NR. So substituting NR1 value and NR2 value here, we get like this. 1 minus S1 into NS1 is equal to S2 minus 1 into NS2. So 1 minus S1 into NS1 means 120F divided by P1, that is equal to S2 minus 1. NS2 means 120 S1 into F divided by P2. So here 120F and here 120F going to get cancelled. So then equation becomes like this: 1 minus S1 divided by P1 is equal to S1 by P2 into S2 minus 1. Further simplification leads to like this: 1 by P1 minus S1 by P1 is equal to S1 S2 divided by P2 minus S1 by P2. Since S1 S2 values are very small, the multiplication value will become very small. So S1 S2 is very small, so S1 S2 divided by P2 can be neglected. So then the equation becomes S1 divided by P1 minus S1 by P2 is equal to 1 by P1. Further simplification can be done like this: S1 into 1 by P1 minus 1 by P2 is equal to 1 by P1. So further it can be simplified like this: S1 into P2 minus P1 divided by P1 P2 is equal to 1 by P1. So then S1 can be written as like this: P2 divided by, so then S1 will become S1 is equal to P2 divided by P2 minus P1. Once S1 is known for the differential connection of the two three-phase induction motors, cascade connection, then the motor 1 speed can be written as NR1 is equal to 1 minus S1 into NS1. So further it can be expanded like this. S1 is known, so substitute P2 by P2 minus P1. So here, so then NR1 is equal to 1 minus P2 divided by P2 minus P1 into NS1. And further it can be simplified like this: P2 minus P1 minus P2 divided by P2 minus P1, that is equal to 1 here NS1 is nothing but 120F by P1. So then this minus P2, this plus P2 going to get cancelled, and then taking this minus P1 into denominator, then this will become like this: NR1 is equal to 120F divided by P1 minus P2, and this P1 is going to get cancelled. So then for the differential connection of three induction motors, three-phase induction motors, then NR1 becomes NR2 is equal to NR, that is equal to 120F divided by P1 minus P2. So let me summarize once this cascade method of three-phase induction motor with two different pole connection. For cumulative type, S1 will become P2 divided by P1 plus P2, and whereas the common speed or shaft speed of the rotor speed of both the machines will become 120F divided by P1 plus P2, whereas for a differential connection of the two three-phase induction motors of two different poles, S1 will become P2 divided by P2 minus P1, and the common speed of both the machines, machine 1 and machine 2, or motor speed, will become 120F divided by P1 minus P2.